Okay, now that we have the fundamental theorem of calculus, we can do some polynomial factoring theorems. So let's start with this one. The theorem is going to be if p of x equals the sum ci x to the I equals 0 to n, is a polynomial with real coefficients and z in C is a root, then z bar, the conjugate of z, is also a root. Okay, so let's prove this. So let p of z equal 0. Then p of z bar is equal to the sum from I equals 0 to n c sub I z bar to the I, which is equal to the sum from I equals 0 to n of c sub I z to the I bar, which is equal to the sum from I equals 0 to n of c sub I z to the I bar. These two equalities come just from how conjugates work, and this one I put the bar over all of the c sub I because the c sub I are real, and the conjugate of a real number is itself. And this is equal to the bar from I equals 0 to n of c sub I z to the I, which is equal to p of z bar, which is equal to 0. Okay. So that's sort of a silly little statement that I found another root that's a conjugate, but what that means is if you have complex roots, they come in conjugate pairs. So this means that every polynomial with real coefficients factors into linear factors and quadratic factors, period. I don't get any cubic factors, I don't have to have any quartic factors or anything like that. Over these should be factors with real coefficients. Okay, so let's maybe show that statement. So the theorem is going to be if p of z, let's say p of x, equals c sub I from I equals 0 to n, has real coefficients, then it factors as product of x minus ri, r equals 1 to k, times the product of x minus, let's say ci, x minus ci bar from I equals 1 to j, and this is a product of these two products, where the Ri are the real roots and the Ci are the conjugate, and maybe I'll put Ci bar are the conjugate root pairs. Okay, so let's prove this. Let Ri be a root of P of x, then x minus Ri divides P of x, say this is sort of by the division algorithm. Say Q of x equals P of x divided by x minus Ri. Then by induction we can factor Q of x, maybe by induction on the degree. We can factor Q of x as above, tack on x minus Ri to Q's factorization. So this is if R was real. If R is not real, then we do the same thing. So maybe let's say be a real root. Otherwise, let Ci be a complex root. Then Ci bar is also a root. So x minus Ci, x minus Ci bar, divide Px, and get Q and a factorization the same way. Okay. I should say that if you want to factor a linear or a degree 1 polynomial, you just have to have the degree 1 polynomial. So the induction step gets started with degree 1 being a linear polynomial, and a line always has a root as long as it's not constant. Okay. And maybe I should say that in the theorem, if P of x has real coefficients and is non-constant, but that's sort of a trivial case. Okay. Why does this let me factor into quadratic factors with real coefficients? Well, x minus Ci times x minus Ci bar is equal to x squared plus minus, I guess, Ci plus Ci bar x plus Ci bar. This is equal to x squared minus 2 times the real part of Ci. Conjugate, when you add them together, the imaginary parts cancel. X plus, this is the magnitude of Ci squared, which is also real. So this is real, has real coefficients. Okay. So why is this useful for us? Well, we can always factor any polynomial into linears and quadratics then with real coefficients, and this lets us work on partial fraction decompositions fairly easily because we can integrate partial fractions when we can integrate rational functions. We sort of know how to integrate 1 over x plus 1. We can integrate that. We can integrate 1 over x plus 1 to the k. That's not so bad. We can integrate x plus 2, for example, over x squared plus 4. This is an irreducible quadratic. It's one of the quadratics you would get from having 2 imaginary roots. We can integrate things like this using a trig substitution, and we can also integrate things like 2x minus 3 over x squared plus 4x plus 16. Let's take that to the third power. We can integrate things like this with trig substitutions and the like. So that's why these partial fractions are useful, and the theorem above says we can always get partial fractions that have sort of these forms, where I have 1 over some linear factor of x to some power, or I get a constant over some linear factor, or I get a linear factor over some quadratic polynomial raised to some power. We can always get those form of things, and these form of things we can actually integrate. Okay, we'll do partial fraction decomposition in the next video.